Hi, I'm Thomas, and today I'd like to take you on a bit of a journey. We'll start out by looking at some very high level stuff, philosophy of science, if you will. We don't usually talk about that because we take it for granted, but if we want to talk about algorithms in practice, we kind of need to talk about what we mean when we talk about algorithms in theory. But then we'll spend most of our time down in the dirt, looking at things we usually ignore, things we sweep under the carpet. Well, now I'm mixing metaphors, but you see what I mean. And that's what makes algorithms so interesting to me. There's beautiful maths, really nice abstractions, but if you care to look, there is also a real nitty-gritty, hands-on engineering aspect to it. To kick us off, I'm going to say some things that are quite critical of the way that we usually analyze algorithms academically. I will question a little bit how we think about algorithms, what we're even trying to do when we analyze them. It's not because I think what we usually do is bad. It's not. I'd just like us all to think a little bit about our basic assumptions, about our theoretical framework, because it's probably been a while since you've really thought about any of this. Why we do the things we do and why we do them the way that we do. When you first learned algorithms and data structures, you probably learned about pseudocode. You start out counting basic operations, though it was probably never made entirely clear what those are exactly and why. But don't worry about it, big O notation shows up soon enough and we won't have to think about it. These abstractions are good. They allow us to get things done. And we most certainly have gotten things done. You've been hearing about it all semester. But we didn't have to do it this way. Nothing about algorithms, data structures, computation. Nothing made us use asymptotic, big O analysis. Well, your teachers made you do it, and they were right to. But I think you probably weren't really in an optimal position at the time to appreciate exactly what was going on, scientifically speaking. In a position to see what an enormous decision it is to do things this way, to care about these things specifically and not others. It was all new and you were kind of along for the ride. So I thought advanced algorithms would be a good opportunity to revisit some of the basic assumptions. Not because they're bad and you need different ones, but because it's good to be aware of them. I know the program promised a lecture about algorithms in practice, and we'll get there, but I think we'll do well to have a quick look at how our theory relates to practice. The legendary Donald Knuth, for example, in his book The Art of Computer Programming, and note that he calls it The Art of Computer Programming, not computer algorithms, even though it is definitely a book about algorithms. He does have an explicit machine model. It's called MIX, or MMIX in later editions. He gives actual bounds in the number of instructions performed. Of merge sort, he says, for example, and I quote, "Thus, about 12.5 units are spent on each record in each pass, and the total running time will be asymptotically 12.5 n log n, for both the average and the worst case." He continues, "This is slower than quicksort's average time, and it may not be enough better than heapsort to justify taking twice as much memory space, since the asymptotic runtime of program such and so is never more than 18 n log n." That's an amount of detail that you don't usually see anymore. We would just call all of this n log n. We'll have a quick look at some sorting later, but if you're going to improve sorting in practice, you're going to have to look at the details quite closely. Interpreting theorems about algorithms can actually be a little bit tricky. These are mathematical claims. They are technically correct, which is, as they say, the best kind of correct. But they are therefore correct only in a very specific way, and sometimes that way is not technically what we actually care about. Sometimes we don't even really think about the theorem quite in the right way. For example, asymptotic runtime bounds with big O notation. I think about those as saying something about how fast an algorithm is. That's a A reasonable interpretation, but technically these bounds hold existentially, stating that there exists some arbitrarily large n0 and some arbitrarily large constant factor. That's what we actually mean by fast when we use big O analysis, which is all the time. There is no claim being made about any finite instance. None at all. Just make n0 larger or make the hidden constant larger. Yet your computer is finite. Asymptotic big O runtime bounds, as stated, technically have no bearing on reality. Calling an algorithm fast on this basis, well, as it turns out, that usually works quite well. But it didn't have to. That's not what the theorem says. That's really quite interesting. Okay, small sidebar here. This can actually be a pretty useful trick when you want to prove bounds. For the asymptotic analysis, you can just ignore all instances up to a constant size. If the answer is computable, you can do it in constant time. F of a constant is a constant. Does your elegant algorithm have difficulty handling a couple of annoying small exceptions? Doesn't matter. There exists an algorithm that's just your elegant one, except it has all of the special cases hard-coded. For the same reason, you seldom have to care about the base case in a divide and conquer algorithm. Well, as long as you're not actually going to implement it. Just make sure you divide it down into computable things of size bounded by a constant, and you're good. So, big O asymptotic runtime bounds are meaningless? Well, no. They're just not about your actual computer. Not technically. I could claim that anything that I can ever run on my actual machine has runtime O of 1 because, and I'll ignore streaming algorithms here, it can only handle instances of a constant size. That's not really a useful claim to make, though. Yeah, it's O of 1. Congratulations, you broke all of the good ideas. Because here's the thing, we have lots of good algorithms. Saying, lol, everything is O of 1 is not useful. It doesn't get you anywhere. I don't recommend it. You should definitely keep using asymptotic analysis and big O notation. We have lots of great theory. But then your theory is about these infinite things, and that's what I wanted to remind you of, because it's probably not something that you think about a lot. How far away these theorems are from saying anything about what anybody does on a real machine. But it works. It's super useful. It's kind of amazing. This may be apocryphal, but the story goes that Dijkstra had a hard time getting his shortest paths algorithm published. So in this paper, he gives the algorithm that you know about, the one that efficiently calculates shortest paths in a graph with non-negative edge weights. It's called A Note on Two Problems in Connection with Graphs. The first one is minimum spanning tree, by the way, though he doesn't use the word and he feels the need to explain. A tree is a graph with one and only one path between every two nodes. This is a super important early paper, but as I said, apparently it was hard to get published. What argument could the reviewers possibly have had for rejecting it? Well, quite simply, the argument was, so what? Who cares? The shortest path problem is clearly computable. Here, I'll prove it for you. Observation. There exists a shortest path that does not contain loops. These would just make the path longer. Here we must assume that the weights are non-negative, but so does Dijkstra. So there exists a shortest path that is simple. The set of simple paths in a finite graph is, of course, finite. So you can just try all of them, see which one is the shortest. QED. Who needs a complicated way to do it? And remember, this is 1959 when it gets published. This is Numerische Mathematik, issue 1. This is before P versus NP by quite a bit. Actually, this is before the concept of polynomial time as efficient. Do you know what runtime bound he gives in the paper? This is too much fun. I'll just read it for you. The solution given above is to be preferred to the solution by L. R. Ford as described by C. Berge, for irrespectively of the number of branches, he means edges, we need not store the data for all branches simultaneously, but only for the branches in the sets 1 and 2, and this number is always less than n. What he's saying here is that the priority queue, as we would implement it today, only ever contains n elements. Furthermore, the amount of work to be done seems to be considerably less. Well, okay. This is 60 years ago, and we've come quite a way since then.